that, or is that too small? All right, so you were given a volume of acetic acid. I think it was 1.5 mil. And isopentyl alcohol is 0.8 mils. Pet peeve number 2. 1 milliliter equals 1,000 microliters. 1 liter equals 1,000 milliliters. 1 milligram equals 1,000 micrograms. Not that you see that very often. 1 gram equals 1,000 milligrams. If you remember that the only prefixes that you need to know are micro and milli, and that they both are 1,000th of the next higher number that you're talking about, you won't get it wrong. It's 1,000th, it's not 100th. There are 1,000 milliliters in a liter. There are 1,000 microliters in a milliliter. Okay? Dead silence. The only 2 prefixes you need to know are milli and micro, and there's 1,000 between each of those types of measurement. Okay? All right, so we have 1.5 milliliters. Multiply that by the density. What's the density of acetic acid? Someone got that page open? Just less than 1 or just over 1? 0.02 grams. We'll make it that anyway, per milliliter. That gives us about 1.6 grams of acetic acid. So you have grams of acetic acid. In order to determine the limiting reagent, you need to convert that to moles. So you multiply by 1 mole of acetic acid per how many grams? What's the molar mass? 63, something like that. 60.5? Okay, so 60 grams. That gives us the number of moles. I think it's like 26 something. 26.3, something like that, from the write-ups. So that's the number of moles of acetic acid. You have to do the same thing, starting with a volume of alcohol. 0.8 milliliters of the alcohol. What's the density of the alcohol? 0.81 grams per milliliter. That gives us 0.64, something like that. 6.4? Yeah, we'll make it that. 6.4 moles of the alcohol. Is that right, or am I off? All right, well, we'll pretend that. Huh?
So 26.3.
That's the number of moles of the acetic acid.
But you divide it instead.
1 divided by 6. All right, so somebody do the math for me. What's 1.6 divided by 60?
0.027.
So, okay, and this is wrong.
I have to message you this somewhere on my lab report, but I don't remember, but I don't have it. I don't care enough to have it up.
This is grams. So this is 0.648. So make it 0.65. All right, so 0.665 grams of the alcohol times the inverse of the molar mass, 1 mole of alcohol.
it cut off.
Divided by what's the molar mass?
I accidentally pressed that for some reason, so I do that.
Should be on that table too. 88. 88.15. Okay. That equals, somebody do the math for me.
Like 0074.
That doesn't sound right.
Why?
But regardless, we know from this calculation, this number of moles of the alcohol and this number of moles of the acetic acid, whichever of the two is less, is the not limiting reagent. Whichever of these two is the most is the limiting reagent. No, that's wrong. You sure this number is right? Is it 0027? Point 0027?
How did you get 1.6? How did you get 1.6 grams?
It's now 1.6, 1.65. All right, well, whatever, you can follow the math. You have milliliters of the acetic acid, that gives you grams of the acetic acid. This is supposed to be grams. Grams of acetic acid divided by the inverse of the molar mass. So whatever the molar mass is that's on your table there, let's take the inverse of that. That gives you the number of moles of acetic acid. Same with the alcohol. You start out with the volume of alcohol, you multiply by the density, which will be given to you. That gives you the grams of the alcohol. The grams of the alcohol multiplied by the inverse of the molar mass of the alcohol. So it's a mole per grams of the alcohol. That gives you the number of moles of the alcohol. Whichever of these two is the lesser quantity, that's the number of moles of the product that you can make. Now, are we good? Everybody can follow the math. Plug in the numbers to make sure that they're right when you get home. But when you start out with liquid, you need to convert the liquid to a mass. You multiply the mass times the inverse of the molar mass of that compound. That gives you the number of moles. Again, you start out with milliliters of the alcohol. You multiply that by the density of the alcohol. That gives you the grams of the alcohol. You multiply the grams of the alcohol by the inverse of the molar mass. The grams cancels the grams. You're left with moles of the alcohol. These are the two components that you added together to form the ester. So whichever of these two mathematical numbers is the lesser quantity, that's the number of moles of ester that you can make. You simply multiply that number of moles by the molecular weight of the ester, and that gives you theoretical yield.
So is that answer not right?
This, I don't know if the math is right or not, but just follow the equation. If you understand the way that the equations are set up, the math will take care of itself. So again, you start out with a liquid. You can either convert the liquid to grams with the density, liquid to grams. You multiply the grams times the inverse of the molar mass. That was grams on the top with grams on the bottom. You're left with moles. That's the answer that you're looking for. Whichever of the two numbers of moles is the lesser amount, that's the number of moles of the ester product that you can make. Now, in the cholesterol experiment, we already knew what the limiting reagent was, so we only had to figure out the number of moles of the cholesterol. The number of moles of cholesterol is the same number of moles as the cholesterol dibromide, so you simply multiplied that by the molar mass of the cholesterol dibromide, which gave you your theoretical yield. Yes?
So the list number is the theoretical yield, or do we have to count them?
Well, if you start out with liquids, you're going to have to take it to the numbers of moles. And whichever of these two is the lesser, that's the limiting reagent. You will always be asked to calculate the limiting reagent. And then the number of moles of the limiting reagents is the number of moles of product that you will form. So you simply multiply that by the molar mass of the product. Are we good? Yes, sir.
Going back to the bromination of cholesterol, will we have to worry about the co-crystallization of acetic acid when finding the percent yield?
If you do, he will ask you to specify that. So if he only gives you the mass of the cholesterol dibromide without the acetic acid, then you don't have to worry about it. I mean, I doubt he would go that route, but just, it's a good question. For that experiment, the infrared spectra, again, there was a carbonyl peak in the IR spectra, and that was from the acetic acid, which a lot of people messed up on. All right, so experiment 10 is just hydrogen bonding. Know what the hydrogen bond donor is? That's the oxygen or nitrogen that's carrying the hydrogen. So either it's a hydroxyl group or it's an amine. The hydrogen bond acceptor is either nitrogen inside of a ring, or carbonyl oxygen can accept a hydrogen bond. You can actually have hydrogen bonds between two hydroxyl groups. If nitrogen or oxygen has a lone pair of electrons, it's capable of accepting a hydrogen bond from a hydrogen bond donor. The donors are always either nitrogen or oxygen that are carrying the hydrogens that are being donated. Okay? The acceptor are either nitrogen or oxygen, but they need to have a lone pair of electrons. So a carbonyl has two lone pairs, a hydroxyl group has two lone pairs. So you can have hydrogen bonds between two hydroxyl groups. Or an amine group in a hydroxyl group. Anything that carrying an electronegative element that's carrying a hydrogen or has a lone hydrogen bond. And some people say fluorine can be involved in hydrogen bonding, but I don't think the lab manual actually goes into that. You probably haven't seen that on lecture yet either. The calculation of the molar mass and theoretical yield and all that nonsense just confuses the matter for that experiment, which really pisses me off why they choose to do that at the end. The yield is just adding the two compounds together rather than converting it to moles, and all the logical steps that you just took a whole semester to learn goes out the window for that last experiment, which is really stupid. But I don't have a say, so.
Still got it.
All right, so we're good with that? So you want to talk about infrared spectra now? All right, so infrared spectra. Infrared light is sort of heat. A heat lamp is actually the energy that an infrared is in the infrared region of the spectrum. So those red lights that shine down on the French fries at McDonald's or whatever, those are infrared lights. The way the spectroscopy works is you have a sample that's inserted into a cuvette or into, they grind it up and put it into a salt pellet that doesn't absorb too much infrared spectra or infrared radiation. And then they shine the light through it, and there's a detector. You see the big peaks? Those are the absorptions. So that's when your compound that is in that cuvette or in that salt plate absorbs that specific energy. And it cycles through a whole range from 3,500, 3,600 all the way down to 500 and 600 at the low end of the spectrum. So the peaks are the ones that come down. It's not the top ones, it's the thing at the bottom of the spectrum. Now, the absorptions that I recommend that you learn and certainly have written down if you haven't memorized them by now are the hydroxyl group and the carbonyl group. The NH group might be something that you should recognize, that's a little bit lower in energy than a hydroxyl group, so lower wave numbers. It's nowhere near as broad and poorly defined as the hydroxyl group is. There's a little bit of definition with a little bit of spikes to the bottom of them. You may be able to tell whether it's 1 hydrogen or 2 hydrogen by the shape of it, but I doubt that's anything that he will ask you about. Moving down the spectrum, the carbonyl peak. The carbonyl peak is generally the sharpest peak in the spectrum. It's somewhere between 1600 and 1750. It comes down to a sharp point and goes back up again. That is something that will help you out with analyzing any of the compounds that carry carbonyls. So there's a whole host of them that you will learn this semester. You have carboxylic acids, you have esters, you have aldehydes, you have ketones, you have amides, if you covered amides, you may or may not have. No? So at least those 4 compounds carry carbonyl groups that will stand out prominently in the infrared spectrum in that region. Yes?
What were the hydroxyl and the NH groups ranges?
Hydroxyl group is a big blobby one that doesn't come down very far, and that's like the highest one that you will come in contact with.
Higher than 3,000.
Like 35, 30. Where's the cholesterol spectrum? That was after the 3-component one. Is the cholesterol one in there? No, he doesn't have one there. But generally, the hydroxyl group has no definition. There's no spikes, or it's not hairy. It's just a blob. And the NH can have a little bit of chop to it, so there might be little sharp spikes. But again, that's lower in energy than the hydroxyl group, so it's a little bit to the right of that on the spectrum. Yeah.
Do you have to know why the graph looks like this way? Like why there's a sharp?
Oh, just know that certain functional groups, when a functional group absorbs some of that radiation, that's when you get a peak. I mean, it's shining light through a salt plate that contains your compound, or a cuvette, a glass sample that contains your compound. Where it's absorbed, that's where you get the peak. If it absorbs strongly, you get the sharp peaks. If it doesn't dissolve or doesn't absorb particularly sharply and just a little bit, that's when you get the big fat hydroxyl group absorption at the height.
So the sharp peak just means it just absorbs as the most?
Yeah, but it's a very confined region, so all of it gets absorbed in that specific. If you broaden that out, it's probably the same amount of area for the hydroxyl group as the sharp carbonyl that goes down a lot farther. So,
We have to know the detail as to why.
no, he won't ask you any specific about the experiment. He'll just ask you to analyze a spectrum, or if there's a sharp peak in the spectrum that he shows you that's got a wave number associated with it, they'll ask you what functional group that is. But again, previous years from what I remember, I think that back page that has the table of absorptions and functional groups, I think that you were able to use that, but don't quote me on that. Don't take the chance on that being the case and then you get in there and not. So at least write down the common functional groups and absorption areas that I mentioned. Don't take my word for it. Any questions about the infrared before we go back? We're good? Okay, yeah. What do you got, Robert?
Where's the lab final going to be hosted? Is it going to be right here?
It's going to be right in the same room.
Right here?
You'll be standing in the lab room, 1029, for an hour or so, writing away. So remember, bring your calculators.
Gotcha.
Don't assume that there's going to be enough calculators for everybody to borrow. I doubt you'll need your goggles. Depending. No? Okay.
We don't?
And
Okay.
your lab coats, probably not. Yes, lab coats or no lab coats? Yeah, no goggles. Okay.
Damn, I
Okay.
threw away my lab
It
coat.
depends on who the head instructor is, whether you have to wear your lab coats. So, are we good? Anybody got any questions?
Thank you for doing this.
Are we? I'm going to be so pissed off if I see questions missed left and right on the calculations. I don't know how many times I can ask the same people the same questions and still. If you have something in the numerator and you have something in the denominator, whether they're on top of each other or they're next to each other or they're 3 factors away from each other, what's in the numerator, if it's the same as something that's in the denominator, you can cancel them out. And that way you don't have to worry about the math. If the units take care of themselves, and it's just a matter of addressing the arithmetic, and it should not be a challenge. And I keep saying it over and over again, and I see a few people with deer in the headlights looks, and I know they're not getting it, and it's very frustrating. So, all right, guys, so if there's nothing else, good luck next week. Hopefully you'll get home and the snowstorm will get bad and classes will be canceled tomorrow.
Thank you, Professor.
Classes are canceled tomorrow. They're probably canceled the rest of the week too. So.
Thank you.
All right, guys.
All right.